Hello friends, I am Amir Nizami and today we are going to study the linear second order differential equations. So let's start with that. So in the last class we have studied the difference between the linear and non-linear second order differential equations, and today we will study the linear second order differential equation with solving the homogeneous and particular solutions. So again, just have a quick revision that we have studied y double prime plus p of x of y prime plus q of x of y, that is equals to f of x. And if this criteria is satisfied, then the derivatives of y, the second derivative, first derivative, and y itself are not having any power or not raised to any power. Okay. And the second point, we can see that the coefficients of the derivatives of y and itself should be a function of x. So here it is a function of x, it is function of x. Here it may be the function, but we have divided it. Otherwise we can say that this is a constant 1, that is coefficient, or x to the power 0, so that is also 1. So it's a function of x with raised to power 0 here. So we know that the coefficients are not having any limitations of power, but only that those coefficients should be a function of x only. So the second point is also satisfied. And the third point, we can say that this f of x, this function that should be right hand side, should be function of x only. Okay, so these all points are satisfied, therefore we are stating that it is a linear second order differential equation, second order differential equations. Okay, now how do we check that whether it is any function is linear or not? So let's, if we have written this y double prime plus p of x of y prime plus q of x of y, so we may state that we give any input to a machine, that is we say that L machine, where L machine we can say that it is a linear, illustrated here as linear machine. So if we give any input y, then this would be the case. So now if we say that L of any constant times y should be nothing but, where c is a constant, c into L times y. If this states, then we say that these functions are linear, where c is any constant. So we will just put, instead of y we will put cy. So c constant times y double prime plus, sorry, here constant times y double prime plus p of x into, instead of y prime you will write cy of prime plus q of x into, instead of y we will provide cy, because we are just using c of y is equals to, instead of y we are providing c of y, so we are putting c of y double prime plus p of x c of y whole prime q of x into cy. So now the constant would come outside with y double prime plus p of x into c into y prime plus q of x into constant c into y. So c here is constant, c we can take c common and we can write y double prime plus p of x of y prime plus q of x of y. So again we can say it that c into L of y, because we have stated that L of y was nothing but y double prime, so it is the same. So we can write this c into L of y. So L of c of y is equals to c times L of y. So this criteria is satisfied. So therefore we say that this is linear function. So to check the function is linear, we should see that if we replace the y with cy, then it should be c times L of y. This criteria must be checked. So this shows that it is linear. This is linear. Okay. If it would be non-linear, then this criteria would not satisfied. If the function that was non-linear, then this criteria should not be satisfied. We can see an example such as if L of y is equals to y into y prime, suppose. So then we see that L of c into y, we replace it. Instead of y, we will provide cy into c times y whole prime. Then c into y into c into y prime. So we will see c square y prime. So it is nothing but c square times L of y. So here we are just giving the input as c of y, and it is giving output as c square times Ly. So therefore this is not linear, non-linear. It is non-linear because here we are having c square. Instead of c square, if it should be c of L of y, then it would be linear. Otherwise it is non-linear. So here it is an example of non-linear cases. Okay. Now, so we may see the another example for the linearity, that if we provide L of u1 plus u2 in two linear combinations, then it should be L of u1 plus L of u2. Okay, so we can see an examples that we will put that example, we can feed it in here, y double prime plus p of x of y prime, or you may state that u double prime plus p of x of u prime plus q of x into u is equals. Okay, let's see with that. So we will just feed instead of u L of u1 plus u2, it was equals to L of u here. So instead of u, we are providing u1 plus u2. So let's see u1 plus u2 double prime plus p of x into u1 plus u2 prime plus q of x into u1 plus u2. Let's resolve it. So it would be u1 double prime plus u2 double prime plus p of x into u1 prime plus p of x into u2 prime plus q of x into u1 plus q of x into u2. So we can arrange it, u1 double prime plus p of x of u1 prime plus q of x into u1, okay, plus p of x into u2, or we can write before that in this format that u2 double prime, we can state u2 double prime plus p of x into u2 prime plus q of x into u2. So it is here u1 double prime plus p of x of u1 prime plus q of x of u1. So we can state here it is a function of L of u1 plus, here we can write this as a function of L of u2. So this is L of u1 and this is L of u2. So L of u1 plus u2 is the combination of L of u1 plus L of u2. So this is also the criteria for checking the linearity. So if this is the case, then equivalently we can also write that L of C1 U1 plus C2 U2 is equals to C1 times L of U1 plus C2 times L of U2. Okay, this criteria would also be satisfied with that. Okay, so now let's start our differential equations. So example 1, solving the homogeneous differential equation as L of y is equals to 0 with homogeneous and constant coefficients. So here the example is y double prime plus 2ay prime plus b of y is equals to 0, and we have to find the solution, general solution y g. We can say that what would be the general solution of this. When right hand side is 0, then we say that the differential equation is a homogeneous differential equation and we have to find its solution. So for solving this, let us try a function or a trial function. We say y of t, trial function, which is equals to e to the power r into x, which is e to the power rx, where r is a constant. Okay. So if we have the first derivative of it, what we will get? If we assume that this is equation 1 and yt prime would be r times e to the power rx, and yt double prime would be r square e to the power rx. We consider this as equation 2. Now we substitute equation 2 in equation 1. So here it is y double prime, so yt double prime we will put there. So r square e to the power rx plus 2a y prime, which is r into e to the power rx, plus by, and b we can see that it's a constant into y is e to the power r of x is equals to 0. So e to the power r of x would be common, r square plus 2a into r plus b, that is equals to 0. So this equation again I will say write it e to the power rx into r square plus 2a into r plus b is equals to 0. So we know that e to the power rx can't be 0 because we have assumed this trial function. Otherwise, if it is 0, then no solution would be there. Okay, So e to the power rx can't be 0, therefore these must be equals to 0. This states that r square plus 2ar plus b should be equals to 0. So therefore we know that these are the quadratic equations, and this can be solved with the equations that r should be equals to minus of b. So minus of 2a plus minus under root b square, that is 4 square 4b upon 2a. So we can say that two roots would be there, r1 or r2. That would be r1 is equals to minus of 2a divided by 2a. So we can say minus 1 minus 4 would come outside, so 4 square root of 4, so that will be 2. So 2 upon 2 upon 2a. A is 1, sorry, here it should be only 2. Yes, then it should be minus of a plus minus under root a square minus b. Okay, so if we are writing r1, then it should be only minus, and r2 would be minus of a minus under root a square minus b, these two roots. Okay, now for these roots to solve, we may have different cases. That case 1, we will say that if this portion a square minus b is greater than 0, then it states that these function roots are real and distinct. Roots are real and distinct. Okay, so r1 and r2 would be like this. Then the homogeneous solution, general solution for this, would be equals to any constant c1 times e to the power r1 of x plus c2 times e to the power r2x. We will get this as a general solution. Case 2, if a square minus b is equals to 0 or a square equals to b, then we have the roots r1 is equals to minus of a, and r2 would also be equals to minus of a. So we will see that two real roots but identical, that is r1 is equals to r2, so that is identical roots. So therefore then, if this is the case, then my general solutions would be equals to c1 e to the power r1x plus c2 into x times e to the power r1x, because r1 and r2 are same, so whether we can consider r1 or r2 any, but this should be multiplied with the independent parameters x. Here we have seen that it was the case here that only constant times this, but here if the roots are identical, then c1 e to the power r1x plus c2 times x into e to the power r1x. This is the difference. And now in the third case, if a square minus b is less than 0, that is, we can say that roots are complex conjugate means r1 is equals to minus of a plus iota times means imaginary number times b of minus a square, r2 is equals to minus of a minus iota times a square minus b minus a square. So these are the two roots which are complex conjugate to each other. Complex conjugate. We say that complex conjugate when the sign of the imaginary number changes. Sign here it is plus and it is minus. So therefore it is a complex conjugate of each other. Plus iota and minus iota. Now we may also refer as R here or R1 here as alpha plus iota beta and R2 as alpha minus iota beta. Alpha here is the real part and beta is imaginary part which is here written as b minus a square and real part is written as minus of a. Okay, alpha is minus of a and beta is under root b minus a square. So we have seen the three cases here. Okay. So let us solve one by one three examples. So now example 1, y double prime minus 4y prime plus 3y is equals to 0. So solution would be, let us take a trial solution. Yt, we are assuming it at e power rx. So yt prime was r e to the power rx and yt double prime would be r square e to the power rx. Then again we will substitute it in these equations and then we will solve, just so we know that. For that we have the solution, general solution of homogeneous solution as c1 e to the power r1x plus c2 e to the power r2x. Now we will see that r1 is equals to minus of a is minus 2 plus root under a square minus b and a square minus b 4 minus 3, that is 1. So we say that minus of minus 2 is plus 2 plus root 1 is 1, that is 3, and r2 is equals to 2 minus 1, that is 1. So one is root is 3 and 1 is 1. So we can say that c1 e to the power r1 is 3x plus c2 into the e to the power r2, that is 1x. So this is the homogeneous or general solution of this equation, c1 e to the power 3x plus c2 e to the power x. It is linearly independent. Constant c1 and c2 which is independent to each other. So this is the homogeneous solution for this equation y double prime. Okay, so now we will see another examples. So now we will start with another example. That is the second example. Y double prime minus 4y prime plus 4y is equals to 0. So if we state this equation, then here we can say 2a is equals to minus of 4. So a is also equals to minus 2 and b is equals to here 4. So we can see that a square minus b should be greater than 0. So here a square, that is minus of 2 whole square minus b, that is 4. So we will check the criteria here. A square minus b, sorry, so here it is minus minus plus 4 minus 4, that is equals to 0. So this is the criteria that a square minus b is 0. So r1 we know that minus of a plus under root a square minus b, and r2 was minus of a minus under root a square minus b. So a square minus b here, that is 0. We have seen here it is 0. So r1 is equals to r2 is equals to minus of a, that is minus of minus 2, that is equals to plus 2. So both root is identical and real. Okay, so we know that the general solution for this equation, that c1 e to the power r1x plus c2 into a independent constant will be multiplied with this e to the power r1x. So c1 e to the power 2x plus c2 into x into e to the power 2x. This is the general solution for this equation. And now we'll see the third example. Example 3. So y double prime minus 4y prime plus 5y is equals to 0. So here 2a is equals to minus 4, that is a is equals to minus of 2 and b is equals to 5. So a square minus b we will see equals to a square, we say minus 2, that is 4, minus b, that is 5, is minus 1, which is less than 0, negative. So if it is less than 0, then we know that the general solution would be how much? E to the power alpha x multiplied by c1 cos beta x plus c2 sine of beta x. This is the general solution, homogeneous solution for this equation, where we know that alpha is how much? Minus of a, and beta, that is equals to under root of a square minus or b minus a square. Okay, so alpha is equals to minus of a, so minus of 2 would be equals to plus 2, and this under root of b minus a square. So b is here 5 minus a square is minus 2 square, so under 5 minus 4, that is equals to 1. So root 1 is 1. So the general solution would be equals to e to the power alpha x, that is e to the power x into c1 cos beta x. Sorry, alpha is 2, so e to the power 2x into c1 cos of x plus c2 sine of x. So this is the homogeneous equation, homogeneous solution of this linear second order linear differential equation. So we have seen all the three cases here. So three solutions for this. This is the most common case generally we come across in the earthquake engineering, where we solve the D'Alembert's principle or the single degree of freedom system, where generally these equations mu double dot plus u dot plus k of u is equals to 0 when we are just studying the free vibration case, that is the homogeneous case, right hand side is 0. So therefore we just divide this m, so u double dot plus c by m into u dot plus k by m into u equals to 0. So this is a constant, it is a constant where k by m is nothing but omega n square. Okay, so now we solve this second order differential equation and we find the solution. So this refers, C refers with the damping case, and K is the restoring force, or Ku is the restoring force, so K refers to the stiffness. Okay, and M here refers to mass. So we find the solution of the second order differential equations. Okay, so most of the cases generally lies in this category. So these are the applications in this domain. We apply the second order differential equation and solve this equation, and we find the response, which is u with respect to t, and that would be nothing but, if we just solve this equation in this sense, then it would be written as e to the power, here the independent function would be t rather x, so here it would be e to the power 2x into c1 cos of t plus c2 sine of t. And now this constant c1 and c2 would be found with the initial conditions. Okay, so we will find it with the initial conditions, that whether it would be given that u of 0 would be 0 or anything, any value, we can say that u of 0 is u naught and u dot of 0 is u dot 0. Okay, so these two conditions would be given. From there we can solve the two unknowns c1 and c2. So these are the applications of these second order differential equations. So there are some special functions when we simply solve these equations, second order equations. So solving now particular solution of differential equations such as y double prime plus 2ay prime plus b of y and right hand side it is not 0 but here any function f of x. Okay, here we are just studying with the constant coefficients. Okay, constant coefficients are, we are restricting constant, and this is a constant, this is a constant, otherwise it may be the function of x, we know that, but here we are restricting ourselves with the constant function for our ease. Okay, so to find the particular solution there are some special cases. Special cases, what are those special cases? First we can say that if f of x is equals to e to power exponential function e to the power mx, or f of x is nothing but sine of mx or cos of mx, any one of them. The third we can say f of x may be an algebraic function x to the power n, where n is whole number. So if these are the three cases we see, then we can easily find out the particular solution. Okay, so with the undetermined coefficients, this method would call the undetermined coefficients if this is the special cases, that right hand side would be these three functions, otherwise we have to go with the variational parameters method. Okay, so here, so we will see one example here. Sorry, that if y, or let me tell you one thing, that if this is the function f, then we will choose our trial function yp would be any constant times e to the power mx, right hand side will be the same. The second function yp would be equals to any constant a into right hand side would be sine of mx plus b times cos of mx. Okay, so here if sine mx or cos mx, then we have to choose here these two, both sine and cos. And the third case here y would be equals to a times n x to the power n plus a n minus 1 x to the power n minus 1 plus a n minus 2 x to the power n minus 2 plus so on a not up to this, and x0 is 1. So this would be the chosen trial functions if the function right hand side is this. Okay, so let's see one example. We'll see one example, that y dot prime minus 4y prime plus 3y is equals to e to the power 5x. This is equation 1. So solution, we know that any solution is a combination of y, general solution is a combination of y homogeneous part plus y particular. So homogeneous part, we know that this is solved when the right hand side is equals to 0, means L of y is equals to 0, and y particular integration is L of y is equals to, here it is given e to the power 5x. Okay, so homogeneous portion, we know here that y of, or we can write here y of homogeneous, we have solved before, that y dot prime minus 4y prime plus 3y, and those cases we remember that the solutions for that. So here in this example, y p, we will take a function a into e to the power 5x. So therefore we will see y prime would be 5a e to the power 5x, and yp double prime would be equals to 25 a e to the power 5x. And we will substitute these are the equations 2, we can say, and we will substitute it back in the equation 1. So what would be that? 25 a e to the power 5x minus 4 into yp prime, that is 5 a e to the power 5x, plus 3 into y, and y is a into e to the power 5x, is equals to e to the power 5x. So 25a minus 20a plus 3a common, e to the power 5x equals to e to the power 5x. So this 5x would be cancel out. 25 minus 20 plus 3 means 8a equals to 1. Therefore a is equals to 1 upon 8. So a is equals to here 1 by 8. So we will put it back in that equation, and we can say that yp is equals to 1 by 8 into e to the power 5x. Okay, and we know y homogeneous solution here. Y homogeneous is c1 e to the power 3x plus c2 e to the power x. So therefore, y general solution is equals to yp plus yh. Yp is 1 by 8 e to the power 5x plus c1 e to the power 3x plus c2 e to the power x, and these are the general solution for this equation. Now c1 and c2, these two constants can be find out by the initial conditions, that it may given that y of 0 is equals to y naught and y prime of 0 would be equals to y prime naught. So these two initial conditions may be given, so we can easily solve these two constants and we can get the solution. And similarly, some functions like sin mx and xn would may be given, and we can also solve those examples. So we can see example 2, y double prime minus 4y prime plus 3y is equals to sine of x. Okay, so we see that it is equation 1. So right hand side is the function sine x, so we take trial function yp equals to a into sine x plus b times cos x. So therefore we can have yp prime, which would be equals to a cos x minus b sine x, and then we can have the double yp double prime function, that it would be minus of a sine x minus b cos x. Okay, and we will substitute it back to equation 1. These are the equation 2 and the above one is the equation. So we can substitute equation 2 in equation 1. So this part we will just put there, yp double prime, and those part, that is minus a sine x minus b cos x minus 4 yp prime means 4 a cos x and plus 4b sin x plus 3y, 3a sin x plus 3b cos x, and that is equals to sine of x plus 0 cos of x. We can cos 0 cos of x. Now we will just say minus a sin x. So all the sin x term we will just gather. Minus a sin x means minus a sin x and plus 3a sin x. So it would be 3a sin x minus to plus 2a sin x. So sorry. So here we will 2a sin x and minus b cos x. So 2a sin x plus 4b sin x and so here 2a sin x plus 4b sin x and any other sin x here? No, that is 1 sin x. So here we can compare 2a plus 4b is equals to 1. Now another equation we can see cos term minus b cos x plus 3b cos x minus 4a cos x and minus b cos x plus 3b cos x plus 2b cos of x is here 0 times cos of x. So we may compare that minus 4a plus 2b is equals to 0. So now we can solve here. So here a is equals to how much? Minus or a is equals to 1 by 2, a equals to 1 by 2 or sorry b by 2, 1 into b by 2. So we can replace it here, that 2 into b by 2 plus 4b equals to 1, 2 to cancel, 5b equals to 1, b equals to 1 by 5 and a is equals to a is half of b means 1 by 10. So a would be equals to 1 by 10. So therefore we can say that y particular solution would be 1 by 10 sin x plus 1 by 5 cos x. This is the particular solution. And the homogeneous solution, we know y of h. For this case we have written before that c1 e to the power 3x plus c2 e to the power x. So therefore we can write y general solution for this as 1 by 10 sin x plus 1 by 5 cos x plus c1 e to the power 3x plus c2 e to the power x. This is the final solution where c1 c2 can be solved, c1 comma c2 with initial conditions. Okay, so we can solve it with initial conditions given there, that y of 0 equals to y naught and y prime of 0 equals to y prime naught. So these two initial conditions will help to solve this constant c1 and c2, and we will get the final solutions. So if these are the cases that we have discussed, that sin x or e to the power mx or cos x or any linear function or any algebraic function x to the power n, then as we have discussed that we will take a trial solution according to that function, and then we will put it and we will get the solutions. But if case is other than other than a special case, if these three cases or four cases, then we can't solve with the coefficient of undetermined coefficient methods. Then we have to go with the variational parameters, and then we have to solve that problem. Okay, just like the examples, we may have examples like y double prime plus y prime equals to suppose sec x, like this. So it is not the special function, because special function was sin x oblique cos x, we can say e to the power x, e to the power mx, or we can say x to the power n. These were the special functions. Other than these functions, then we can't solve with the undetermined coefficient parameters. Then we have to go for variational methods, variation parameters method. There we have to solve this problem with the help of this. Okay, and if the coefficients are not constant, then those solution would be found with the help of the series expansion method, for power series method. Okay, so thank you for this lecture.